Hidden under the seed coat are all the resources and the DNA coding to start the life of a new plant. The healthier a seed is, the more likely a vigorous plant will develop. And seeds within a sample are very similar but also slightly different. How and why are seeds within a sample slightly different? How to select the seeds that will yield plants with desired phenotypic traits? These are just some of the questions that can be explored based on deployment of advanced imaging technologies. But before analyzing seeds, let's start with some important reasons why advanced imaging stands out as a promising technology. It is non-destructive, meaning we can collect data without damaging the seeds. We can do it fast, sometimes in real time, and we get very repeatable data. We get the same results over and over, and we get quantitative data. Advanced imaging or machine vision can be used in several ways throughout the seed supply chain. The topic of this video is to provide introductory insight into image-based exploration of seeds. But in general, we can use it for classification and sorting of seeds. We can use it in different ways to perform quality control. And finally, as part of seed exploration, finding out about the variance and the uniqueness of some of the seeds within our samples. And when we talk about image-based exploration of seeds, it can serve many different important purposes. We can look at within sample variance. We can try to identify outliers within a sample. We can look at between sample variance, and we can also try to find clusters among multiple samples. In different applications of advanced imaging technologies, there are several key priorities to consider. We have to make sure that the data is repeatable, and that has to do with lighting conditions. We have to make sure that the classification accuracy is high, that our classification algorithm has high level of robustness and sensitivity, and in some applications we may also need the system to perform at a high speed and therefore be able to process large amounts of data. All of those priorities are linked to the spatial resolution and the spectral resolution of our data. And in this video, we are particularly interested in showing the importance of spectral resolution. If we look at some data, suppose we are placing seeds on a running conveyor belt and image them individually in a straight line. Imagine that each seed is captured as a single image with a serial code and being associated with each image and the background being removed. For illustration of this, we're showing 5 hemp seeds acquired with our imaging system. And you can see that the 5 seeds are very, very difficult to tell apart. We can average reflectance values from each seed. And with an RGB camera, if that's what we are using, we only have 3 channels, red, green, and blue. And we would therefore get 3 bars per seed. One way to illustrate variance among the seeds is to divide the maximum and the minimum of the 5 seeds. And that's what these red dots are showing. The closer to the value 1, the smaller the variance. And we can see that the red dots show that the 5 seeds are very similar in the blue channel, only about 9% difference, while there's about 16% difference in the red channel. If the same seeds had been imaged with a multispectral camera with 19 channels, then we have higher spectral resolution and several channels appear as good indicators of variance among the seeds, again with the red line showing the difference between maximum and minimum. But we can go even further. Imagine that we use a hyperspectral camera with 150 channels. It is here clear why high spectral resolution is important in the exploration of seeds. Now that we have learned a little bit about the importance of hyperspectral imaging, let's image 100 seeds from each of 5 samples, so 500 seeds in total, and let's explore how the imaging technology can be used to identify outliers and quantify variance within these samples. If we start with examining data from a single sample, we can examine the overall variance by looking again at the maximum minimum ratio in the 150 spectral bands or channels. We can see that some spectral bands show much more variance than others. But we can also plot individual seeds based on their similarity. The further apart they are in this plot, the more different they are. This method can be used to identify outliers, and this simple analysis suggests that a few seeds are very different from the remaining 96 seeds in this sample. Such seeds would be prime candidates for further and more detailed analysis. Advanced imaging can also be used to examine variance based on seeds originating from plants grown at different locations, in different growing seasons, or after being stored under different conditions or over time. In other words, how consistent or robust are seed samples in response to different variables? Here's an example of 100 seeds of the same genotype but grown under two different conditions. Generally, the samples overlap, but each sample also has its own set of outliers. Again, such outlier seeds could be subjected to more detailed analysis to get a better understanding of how growing conditions affect hemp seeds. And then we can look at a scenario in which we wish to examine 100 hemp seeds from all 5 samples. In other words, 500 dots, as shown here in this similarity plot. The similarity plot shows that most seeds, irrespectively of sample ID, are grouped together and therefore similar, but each sample also has a few outliers. We can classify the 500 seeds based on their original sample ID, and we can see that we get about 40 to 75% of seeds being correctly classified. But that also means that sample ID is not a very strong classifier in this case. Overall, the seeds are more similar than they are different, but we also see that different samples have similar outliers. And maybe those outliers represent seeds with unique phenotypic traits, so we might be interested in identifying them across sample IDs. And to analyze seeds across sample IDs, we can perform cluster analysis, in which we group the seeds into a certain number of clusters. In this case, we have divided the 500 seeds into 5 groups or clusters, and it is seen that the small red cluster of 7 seeds is uniquely different from all the other clusters. It turns out that the 7 seeds in cluster 5 are mainly from 2 seed samples, R2 and YS. If we now go all the way back and look at the average profiles of the 5 seed samples, we can see that they are quite similar but generally divided into 2 groups. But we can also look at the average profiles of the 5 clusters, and we can see that they are very different and therefore capture much more of the variance than the original sample IDs. This means that cluster results can be used to inform costly and time-consuming molecular and staining procedures. Time, money, and resources can be saved when such procedures are guided by results from advanced imaging analyses. With this brief video, we hope we have convinced you about the potential of advanced imaging as a technology to assist and complement a wide range of crop breeding and quality control procedures. To acquire more information about within sample variance, about outliers, about between sample variance, and about clusters among samples. If this has sparked your interest, then we hope you will visit our website and contact us directly for more information.